Okay, so I'm Jeremy. I'm, I guess, taking over from Ugo at this point and beginning the second topic, which is about neural network theory. So the structure of this topic is another six more lectures. The first two lectures are like introducing tools to like help you understand neural networks. So you might come away wondering like why you learned this stuff or why it was useful. And the first homework is going to cover these tools again. But then after that, we're going to apply the tools in the lectures after to think about optimization and generalization. And yeah, there's two more homeworks, and we'll post the first one on Thursday, and it's due the week after. So today, I'm going to start thinking a little like philosophically, like what's the point of theory and like what is it good for? Then I'm going to go over the basics of like deep learning, but I'm going to assume that you're already like somewhat familiar and like maybe you took 155. Then we're going to like think about like what are the motivating questions, like what are people interested in these like theoretical questions about neural networks at the moment. And then like the main topic of the lecture is like thinking about architecture design, and then there's going to be something on perturbation theory at the end. So okay, let's get started. So like why theorize? Like what's the point in this? So if you talk to people about why they do machine learning theory, like some of the things that you'll hear, like one is that people like math and that's why they do it. And another thing you sometimes hear is somebody tells you that like you couldn't possibly use an algorithm if you don't have a guarantee, like a mathematical guarantee. And in deep learning, like it's like not really true because people use these algorithms all the time, even though they don't have guarantees. But these are like some motivations people have. For me, and like I guess motivating what I put in the lectures is like trying to build a better understanding of what works, because often stuff in machine learning works really well and we don't exactly know why. And then hopefully we can then improve what we already have and we can also build on it. So like if you want to combine deep learning and control, then like having a really rigorous understanding of like machine learning and deep learning could help you do that potentially. So I want to claim, or like what like I think that theory goes through several stages, or it should go through several stages. So I just wanted to like talk briefly about what those are. So there's like, it begins with like empirical exploration, like you have this system that's like complicated and you didn't understand it, so you like play around with it and you get a feeling for how things work and what might be important. And then you have to like build a model, and there's this, so that's like a description of the system that you can like deal with, but it's like throwing away some information. And there's that like the famous quote that like all models are wrong, but some are useful. And the claim is that like often in deep learning, we actually don't have good models yet, making it hard to do theoretical stuff because we haven't done that modeling stuff. And then once you have a model, you can like derive results, which might be useful to you. And then finally, you can go back and test out the results empirically. And there's like some caricatures, because like there's some researchers will like stay entirely in this like experimental loop, which is still quite useful. And then there are people who will kind of work entirely in this like world of like deriving things, like taking what models we have and just like deriving stuff. And there's this XKCD comic, which is about kind of like a caricature of like the state of machine learning, where they say this is your machine learning system. You pour the data into this big pile of linear algebra, then you collect the answers on the other side. What if the answers are wrong? Well, then you just stir the pile until they start looking right. So obviously this is a caricature, but there's like a grain of truth about like how some stuff goes. And then at the other end of the spectrum, there's like just where you're just like doing theory and you're just deriving stuff, and you never get to test, you never get around to testing it empirically. And that's like the caricature of the string theorist. But anyway, that's the philosophical portion out of the way. So now I want to like review the basics of like neural networks. So I think a good place to start is with the artificial neuron. So the idea of the artificial neuron is that you have this thing that has some inputs and it has an output. And we call the inputs like x1, x2 up to xd. And the output is computed as like a nonlinear function of a weighted combination of the inputs. And what is this like nonlinearity? The classic example is called a ReLU. So phi of x is defined this way. And if you plot what this looks like, if you plot the input to the nonlinearity against the output, like if the input is negative, then it returns 0. And if that input is positive, it just passes the input through. So it's pretty much the simplest nonlinear function you could imagine. It's also like the one that works the best in neural networks. And the final thing about the artificial neuron is that it has a geometric interpretation. So the idea is that let's see. By the way, if I say anything that is confusing, just like, yeah, definitely ask questions and stop me. Otherwise, I'll just like keep going. But so if you imagine that there were just two inputs, so there's x1 and x2. So this is like the inputs to the neuron, and you plot them on this graph. Then if you look at the weights, so you would have like w1 and w2. You can plot the weight vector, we'll call it w, and you can think about the hyperplane that's like perpendicular to this weight vector. And what the ReLU neurons does is, if the input like x1 and x2 lie on this side of the hyperplane, then it returns 0. And if the inputs lie on this side of the hyperplane, then it returns like W transpose X, which is like the projection of the input onto the weight vector W. So you can think about like neurons in terms of hyperplanes, and it's like particularly simple when the nonlinearity is like the ReLU nonlinearity. Okay, so this is the neuron. The next thing that you do is you like take neurons and like compose them to build networks. So to like illustrate that, I'm like gonna do this. So like this is what I would call like a network layer, because it's like there's multiple inputs and multiple outputs, and then you can like have multiple layers. So the idea is that we started with a neuron and we end up with a network. And in machine learning, this will be like a directed acyclic graph, meaning that like you have inputs and you have outputs, and there's no loops to get from the input to the output. They're not allowed. And like when we've like framed it like this, as like taking neurons and like building them up to get networks, like a natural question is like, how do local properties of neurons translate to global properties of the whole network. And like one aspect of that will like address this lecture. But it's something like a good question to keep in mind. Okay, so in machine learning, like we want to train a network to do something useful. So the idea now is that we're going to pass like inputs, which we'll call X, into the network, and we'll get out an output f of x w. So w is like summarizing all of the weights, and f is like representing the network function. And then there'll be a target y. So in machine learning, we have a whole data set. So we're going to denote that as like x, I, y, I running from 1 to capital N. So there's capital N data points with labels. And the idea is that, oh yeah, sorry, we're using this like superscript notation to like denote separate data points, whereas like subscripts will denote like different components of the same data point. So once you have got your data set, then like the thing you do is you make the loss function. So for simplicity, we can think of like mean squared error, which is just like the difference, the squared difference between the output of the network and the target summed over the whole data set. And then like obviously, well, then the next thing you do is that if you want to train the network, you can just use gradient descent, which we can denote like this. So we map the parameters w to w minus eta times the gradient of the loss. So hopefully this is all familiar. But what I want to point out now is that there's like already a question which people don't really know how to answer that well in general, which is like, what is this number eta? Well, it's called the learning rate, but like, how small should it be? Or like, what does it mean? And people don't really, in general, people don't know. And like if you actually train your own machine learning system, you just have to tune this number. And there's several other numbers that you just like tune, which means you try a whole grid of different possibilities and you just see which one works the best. But yeah, like this is like something that we'll actually study in like 2 lectures time, and like try and have a better answer to this question. And like these are the types of questions which, you know, like one day, like all this like hyperparameter tuning and all this kind of thing, you would hope to not have to do that. So that's like okay, we'll get to that in later lectures, but that's just to motivate that like even now, like a few slides in, you already get to questions that like aren't that well understood. So I've called this slide like a global view on backpropagation because to emphasize that I've just said like you take the gradient of the loss function and you use that to update the parameters. But on the next slide, we're going to look at what I've called a local view, because it's actually going to look at how you compute the gradients. And in particular, like from the perspective of a single neuron. So like you can imagine that you're a neuron, like what does the backpropagation algorithm look like from your point of view? So this equation is called the forward pass for a neuron, because it's just telling you how the neuron like computes its output as a function of its inputs and its weights. So the notation here, this is supposed to represent like hi of l plus 1 is supposed to represent the ith neuron in layer L+1. And then this is the activity of a neuron in the previous layer. And the thing I wanted to emphasize is that if you think about this neuron like in the way that we've been drawing it, in the forward pass, like if we're looking at this neuron, it aggregates to compute its output. It aggregates over these neurons, which are called the fan-in neurons. But now if we look at the backward pass, which means like when you're computing gradients, so I've just written down the equations for the backward pass. Like I'm not going to like derive them in front of you, but the idea is that the backward pass happens in 2 steps, which is why there's like 2 equations here. So there's like step 1 and there's step 2. And in step 1, what we're computing is the derivative of the loss function with respect to like the output of a particular neuron. And the way it gets this thing is by aggregating gradients over the fan out. So this is the main thing I wanted to emphasize, is that whereas in the forward pass, the neuron aggregates over like the fan-in neurons, these ones, in the backward pass, what you do is you assume that the fan-out neurons have already computed their gradients. So that in this equation, that's these things. You assume they've already computed them. And then this neuron gets its gradient, which is this term, by like a weighted sum of the gradients of the fan-out neurons. So I just wanted to emphasize that there's like a symmetric structure, like to backpropagation versus forward propagation, where in forward propagation you aggregate inputs over fan-in, and in backpropagation you aggregate the gradients over the fan-out. And then in the second step, the neuron takes its gradient, which is now written here, and it uses it to update its weights. So the idea is that the weights on the fan-in edges are denoted by, like, their gradients are denoted by this term on the left, and like their updates are like proportional to the size of the gradient with respect to like that neuron's activity. But I'm not sure if I've explained it that well, but anyway. Yeah, so forward propagation is like aggregation over fan-in, whereas like backward propagation is aggregation over fan-out. Okay, anyway, this is like my intro to learning in neural networks. But now we're gonna like discuss like what are the questions that people really care about at the moment, or like what are like some of the questions that people are confused about. So the first topic is optimization. So how do we design like principled training algorithms for neural networks? So if you've done like deep learning yourself, you basically, how it turns out, there's like 2 optimizers that people really use a lot, called SGD and add-in. And people don't really know like that, like when they should use one over the other. So you basically like you try both and you see which one works better, and that's the one you go with. And then there's even more optimizers. So like sometimes you try those other ones too. So we're not really at a point where there's like a principled way to make this kind of decision, but that's like what you would hope for eventually. And then if you like dig into like the theoretical literature on optimization, you find that there's all this like work on classic optimization theory, which is like really well developed, but it's like not applicable to deep learning. So there's this kind of like break where, yeah, we don't, in some ways we don't know how to like move beyond that classic optimization stuff. So for example, things like convex optimization. So like how do we, like people want to know like how do we move beyond those like classic ideas and like have more modern ideas. Okay, and the next
question.
Yeah, sorry.
What would be an example of something that's not classic optimization?
Yeah, I guess I just mean by classic, I just mean like the stuff that we already have that yeah, I mean
Can I
like
take a stab at answering this, Jeremy?
Yeah, please.
Yeah, so what you learn in ACM 113 is what I would consider classic optimization theory. Not other optimization theory that's sort of more modern include, in fact, some of Venkat Chandrasekaran's work right now on like sum of squares optimization, Signomios, polynomial-based optimization, etc. And then there are people working on, decentralized optimization based approaches, such as generalizations of like alternating directions method multipliers. But classic centralized global optimization based off convexity is sort of the bulk of classic optimization theory.
Yeah.
Oh, thanks. Okay.
Yeah, that's a good point. By classic, I just mean that like there's all these old papers which make very generic assumptions about like the optimization problem you're trying to solve. Whereas like when you're training a neural network, you're solving a very specific optimization problem. And like the thing that I'm interested in this class is like, what is that structure and like, how do you exploit it? That's what I mean to say. Okay, the other thing is generalization. So like there's some specific questions, but it's like the main question is like, why does machine learning work? And what I claim is that you never actually get taught that, like, because actually people don't agree on actually like the core question is like, why do machine learning systems generalize? Like actually people don't know, or like there's different theories and they're competing with each other, but the question is still not settled. So like, yeah, you have some training data and you train your neural network and it definitely does generalize, but why is that? And some of like the things which like illustrate the points people don't understand is that there's a lot of classic statistics which says that you should never have more model parameters than you have training data. But when you train neural networks, you can often have like millions of parameters, and even you can go down to even like hundreds of data points and things still generalize. So like there's something going on which is like not explained by like a bunch of classic statistics stuff. Right, I'll be a bit more like formal about that later on, but for now it's just like motivation. And then also why do neural networks generalize when they have the capacity to fit any labeling of the training data? Which means, so what people have shown is that you can take a data set and you can randomize all the labels. So there's no relationship between like the inputs and the outputs, but the network can still learn to, sorry, not learn, it can still memorize that labeling. So there's a classic theory of generalization called like VC theory, or it stands for like Vapnik-Chervonenkis theory. And like the premise of this theory is that the function class can't do this. So the fact that neural networks can do this means that like this classic theory is like vacuous for neural networks, like meaning the generalization bounds it gives you don't actually guarantee any amount of generalization. So this is like, it's like an interesting thing. And that's something we're going to look at. Okay, so this is like all the motivation out of the way. So for the rest of the lecture, we're going to talk about like neural architecture design and like perturbation theory. So the classic neural architecture is like a multi-layer perceptron, which has inputs. There's like weight matrices. And it's like if you just took a big product of weight matrices, that would just be itself a matrix. So to stop that happening, you put these like non-linearities in between. like we talked about, like really non-linearities, and then that's how you get your output. And generally, like people use this architecture if the input is just like a vector, or you don't really have like a structured input. But an example of structure in the input is if you're dealing with like images, like if you're, and in that case, people will often use convolutional networks. So the point is that images have translation invariance, and what that means is that if this is an image of a person, if you translate the image, it's still a person. And the idea is that convolutions are like designed to like exploit that structure. So if you think about like, let's look at this example of an image at the bottom, and it's like got d pixels by d pixels. If you treated that using an MLP, using like a standard neuron, since there's d squared pixels, you would have like d squared weights per neuron. So like an MLP neuron would have like d by d weights. But with a convolutional network, what you do is like you take a smaller filter, which is like k by k, and then you just convolve that with the image. And what convolve means is that you sort of pass it over the entire image. And the idea is that, well, there's like two things that people say about this. Like one is, well, the number of weights per filter in a CNN is just k by k. So it reduces the number of, if you think about it, it's using less weights. Obviously, like computationally or like memory wise, having less weights is good. But people will also tell you that like this is a reason that CNNs like generalize better than MLPs. But there's something like suspicious about that argument, because we've already said that like it seems that parameter count doesn't matter for generalization. So that's just something to keep in mind, is that like, yeah, CNNs have less parameters, but is that really the thing which makes them better? And the other reason they're better is that, or that people say, is because, right, like you apply, the fundamental thing is that you apply this filter like at this patch of the image, but you apply the same filter at every other patch. So it's somehow respecting the fact that there's no difference between like the image distribution at like different spatial locations within an image. So how that would get expressed, like the kind of comment, like the kind of things people say is like a CNN is a better inductive bias for images, in the sense that it's designed to respect the structure of the data. But people usually don't actually formalize, they don't formalize what they mean by inductive bias. So there's not like a mathematical formula where you can say, because I've evaluated this formula, I know that this is a better inductive bias. It's more like an intuitive statement that the architecture respects the data. But so one of the things that we're going to try and do in this portion of the class is like formalize those kinds of statements. Like, what is an inductive bias? Anyway, okay, so at this point, there's like a whole zoo of architectures. So if you have
a question before you move on from
yeah, please do.
I'm just wondering what's like I like the overview you've given, and I'm just curious if there's like connections to the Fourier transform that they like talk about when they talk about CNNs, just because I know that, I don't know, that's when I used convolutions. Maybe that's a super naive thing to say, but I was just wondering if people talk about that. Or
right. Yeah, I mean, like both Fourier transforms and convolutions involve like integrating over space or like over the dimensions of an image. But like I think like I'm not an expert on this, but there's like something that people say is that like if you inspect the filters in a trained CNN, like some of the early ones represent like Gabor filters, and that this has something to do with like wavelet transforms. But yeah, if like that should give you something to Google, but I don't know how to say anything more than that. But yeah, like it has may have some relationship to like wavelet transforms rather than Fourier transforms. But
Okay, thanks.
Anyway, okay. So at this point, there's like, if you have data with a certain structure, like the rule of thumb is you use like a certain architecture. So to give you the classic examples, it's like if you have vector data, then you're using NLP. If you have image data, you'd use a CNN. And if you have like sequences, like sequences of words or something, then people use transformers now. But these are just heuristics. So like, yeah, anyway. There's something like one like area of research where people try to go beyond and like try to design new architectures is called neural architecture search. So I'm just going to talk about this briefly, but this is a computational approach to finding new architectures. There's like two main variants of it that I'm aware of. Like the first one is just involves like training a lot of slightly different network architectures and seeing which ones work the best. And that's like so it's like heavily computational. And then people try to do, okay, and see which one works the best. Then there's like a second approach, which I want to point out, which is they try to do everything in one go, meaning you like both train the network and train the architecture. And the idea is that they represent the architecture as like a mixture of different architectures with different weights. So you'd have like alpha 1 times like architecture 1 plus alpha 2 times like architecture 2. And then like you just treat the whole weight vector as like alpha 1, alpha 2, and the parameters of both architectures. And you just try and learn all the, you just train all those parameters by gradient descent. And then at the ends, you like prune away the smallest alphas, and then you're just left with one architecture. And like there's a technique called darts, which does this. But that's all I want to say about architecture search, because this is like a theoretical class, but because what's missing with these techniques. So with search, it's like highly computational. Like it doesn't give you like insight about, say like insight missing. Like the search like gives you some new architecture, but you don't really know why it was better. And there's a final point. Which is that, oh yeah, the results you get are biased by how you set up the search space. So if you look at like the like dramatic results of like people finding new architectures, so the results are biased by how you choose the search space. So like a major example is like the transformer, which is like driving like loads of progress in like natural language processing and lots of other areas. But this wasn't found by neural architecture search. This was found by like people having ideas about what might be better. So it seems like architecture search can like slightly boost the performance of an architecture you already have, but it may not be the way to find like dramatically new architectures. But so there's this other process of finding architectures, which is like human intuition. And this is like how we design CNNs, and it's like how we design transformers. But there's still something missing about this, which is that it's like not very formal. And we don't know how to make statements ultimately we want to be able to make statements like using architecture X to learn data set Y will require Z training samples. Like if you could say something like that, it would be incredibly useful because you would know exactly how much data you needed and all this kind of thing. But we like this intuitive approach to designing architectures, it doesn't tell you what the inductive bias really means. And then it's hard to like go beyond just like experimenting and seeing what works, which is obviously good and it's the place to start, but you might hope for more. Okay. So up until now, we've been talking about like global properties of the architecture, like things like comparing convolutional networks and multi-layer perceptrons, and like talking about like the kind of like overall topology of the network. And we haven't really like resolved anything at this point, but it's something we're going to come back to in the rest of the lectures. But now I want to take a break and talk about local properties of the architecture. So what this means is like that question of like, how do properties of individual neurons affect properties of the whole network? Which is actually quite important if you actually like build your own neural network. This is something you do have to pay really close attention to. So there's a main heuristic which is the really important thing, which is like the driving principle behind how a lot of things work, but in like when you build a neural network. But the heuristic is that if you take two neurons, so like look at this neuron and this neuron, you want to make sure that that activity is on the same scale. So what that means is that the typical range of outputs of both of those neurons, like one should not dominate the other in terms of like how large they are. And if you set up the network to, well, it's actually important that you take account of that to be able to train the network at all, like assuming it's sufficiently deep and it's sufficiently complicated. But so if you want to match the scale of this neuron to the scale of this neuron, like there's a kind of way you can do it recursively. So that's what we're going to look at. So what you do is you imagine that you've already like kind of balanced the scales of the neurons in the previous layer. Well, then the question just becomes, given that the scales of these neurons are balanced, how can I make this neuron be on the same scale as its inputs? Because if you do that for this one, and then you also do it for this one, like then these neighbors will be on the same scale. So like that's the idea. Okay, and it's written here. We don't want the activity of neuron A to dominate the activity of neuron B. So now I'm going to like show you techniques that actually achieve this.
Jim, can I ask a quick question on that?
Yeah, go ahead.
I just, from 155, I remember hearing a comment that occasionally I guess, I don't know if we do want this, but like I know occasionally there's like a technique of like identifying the dead neurons to determine like which areas are important, what aren't important. Like is it kind of a technique to determine how many neurons you need, if I remember correctly? Like, is this all? I guess what I'm trying to say is like, is this always something we want to do, or is it occasionally the case where we do want to let some neurons dominate and say, okay, those are the important ones, and we'll ignore the rest for like computational efficiency?
Oh, that's a good question. So like you might want to prune away like neurons at the end, and like yeah, there's a lot of people look at doing that. What I claim is that like, I don't know if you know, but there's like standard initialization schemes that everybody uses to train neural networks, but like not everyone actually looks into the details of how they work. So one is called Xavier, but it's like if you just like train a neural network in PyTorch, it uses this technique to initialize the weights. And the idea is that this technique is actually doing this process. And if you don't use that initialization, like if you just come up with your own initialization, which isn't worrying about these details, you probably actually won't be able to train the network. That's like my claim. So it's like, it's one of these things which is like taken care of for you, so you don't know about it, but it's actually like an important detail.
Can I make a brief comment?
Yeah.
Yeah, so you may recall from CS 155 when we first talked about gradient descent, that if you set the step size too large, you will oscillate and never converge. That's from one of the first couple of lectures. And that's because the gradient magnitude was so huge. So the choice of the step size depends on the gradient magnitude, right? So those two things are interacting. So if the step size times the gradient magnitude is too large, then you oscillate and you never converge. What determines the gradient magnitude? Well, the size of the function, the function, right? So another way of looking at what Jeremy is saying is that for these really complicated neural networks, if you don't initialize the weights properly, the gradient magnitude is huge. And then it's really hard to tune the step size in the way that you get learning.
I see. This is like basically making a technique to make sure that we are initializing in an initial state for the network where useful results will arise and not like some weird off normal behavior. You get like,
so if I initialize all the weights at like plus or minus 1 million, you set your step size to be 0.1, you won't converge. The gradients are huge.
All right, thank you.
You would actually, if the weights are really large, the gradients shouldn't they be really small, because the same size perturbation of a really large weight would have a smaller effect on the network output. I think it actually works inversely to how you expect, but
yeah, you might be right. I'm thinking on the fly. You might be right. I might have gone the opposite.
Right.
But either way, the initialization is very important for that reason.
Right. Yeah. Yeah. So we're going to deal with optimization. So don't worry if this is confusing, because we're going to deal with optimization in like 2 lectures time. But for now, just like the claim is that like the scale of things is very important. And if you're actually like building a network yourself and not just like taking what PyTorch gives you, it's like something that you have to pay attention to.
That brings up another question about step sizes. I know like a lot of like a lot of results on like say stochastic gradient descent and everything, like they depend on using like step size that depends on the time t. Is there something similar for like when you like train neural networks? Is that like in practice do people do similar things?
So like setting the step size and like decaying it with time is like an important detail, but basically what I would claim is there's no connection between like how it works in practice, or like how you have to do it in practice, and those theoretical results. So like usually those theoretical results are like not about neural networks. It's like convex functions, or like they assume some but anyway, mainly like we're going to come to optimization in like 2 lectures. So yeah, we'll talk about it then. Okay. But so, okay, the thing that I want to say now is, right, I'm going to show you a way of like scaling the weights such that like, given that the inputs to a neuron are on a certain scale, the outputs are on the same scale. So the idea is that we have a neuron. It has some inputs, x1, x2, up to xd, and it has an output. And for simplicity, I'm just going to take the linear case, so there's no non-linearity. So this is like the function of that the neuron implements. And what we need to do is, because we're interested in the inputs being on a certain scale, we have to make some kind of, we have to make some kind of assumption about the scale that they're on. So we're going to assume that the inputs are drawn from a distribution that has a particular scale. So suppose that the inputs are drawn basically such that like x1, x2 up to xd have the same mean. So they have mean mu. They each have the same variance, sigma squared, and the separate inputs have zero covariance, if that makes sense. So the covariance between input 1 and input 2 is 0. And for all pairs of inputs. So that's like the assumption that we're making on the inputs. And now we can study what is under these assumptions, and given a weight vector W, we can study what is the distribution of Y, like what's the distribution of the output. And that gives us information about like how the properties of W affect, like how the properties of the weights and the scale that the weights is on affects the properties of the output. So before we do that, I just want to like kind of go ahead and impose two conditions on the weight vector. So the first condition I'm going to impose is that the sum of the weights is 0. So that means that like the magnitude of the positive weights equals the magnitude of the negative weights. And the second condition I want to impose is that that the sum of the squared weights is 1. So this says that the weight vector lies on a unit hypersphere. So this is like a hyperspherical constraint, and this is like a constraint that the sum of the weights is 0. And given these two conditions, like what I'm going to claim and what you actually show on the homework is that the expected value of Y, the expected output, is 0 by condition 1, by the first weight constraint. And that the expected value of Y squared, which is like the variance of Y, is equal to sigma squared, following from condition 2. So the point of this slide is that if you have inputs with variance sigma, and if you apply these constraints, then the output also has variance sigma squared. So given that the inputs have a certain scale of their variability, you apply some constraints on the weights, and you get outputs with the same variability. So like by scaling the weights, you can make the inputs to a layer have the same scale as the outputs to a layer. And you'll do this calculation in the homework, so hopefully it will be clear. Right, and like what I was saying before is that if you use like the standard PyTorch initialization, it's actually like roughly approximately satisfying these constraints, although not exactly. But it's kind of nice to think about these constraints explicitly, because now if you like, when we jump ahead to like thinking about learning algorithms, you can actually like train neural networks with all the neurons constrained to hyperspheres. So it's just like good to have a picture in your head of like what scale the weight should be on, and that's what these constraints are telling you. Oh yeah, go ahead.
How related is this to like batch normalization?
Yeah, it's really closely related. So I haven't mentioned batch norm, but basically batch norm is like an active technique which actively normalizes the activations to have mean 0 and variance 1. And you can think about this as being like a passive way of getting the same effect or a similar effect. Yeah, like yeah, it's really closely related. I'm putting all, by the way, I'll put references to like these things, including batch norm on the course website. But there's a paper from like DeepMinds that was like came out like 2 months ago, and it's like using these constraints and the technique I'm going to show you on the next slide, and they're like trying to get rid of batch norm just by imposing constraints. But okay, so the thing is that this neglected the non-linearity. It just instead assumed that the neuron is linear. So now let's ask, like, how does the non-linearity affect things? Right, the standard non-linearity is like ReLU. So in X, like, remember that like if you have a neuron, the non-linearity like acts on the output. But so now you can think of, right, really like X is what we've been calling Y. So I'll just call it Y. So Y is like the output of a neuron. And this is the definition of ReLU. So now let's make an assumption about the distribution of Y, and then we can study how the output of the nonlinearity, like the distribution of the output. So suppose that that Y is distributed normally with mean 0 and variance sigma squared. So remember that on the last slide, we actually showed that under these constraints, at least under these conditions, that the mean would be 0 and the mean of the linear output would be 0 and the variance would be sigma squared. So like we're sort of taking those conditions and now making a further condition that the output is also normal. And like, remember, like this is just a model. So like probably the outputs aren't actually normal, but you at least learn something by studying the model. Okay, so we're assuming that we're passing a random variable through a nonlinearity and the random variable is Gaussian. What's the distribution of the output of the nonlinearity? Well, if you think about, if you plot Y, like the distribution of Y, well, it's Gaussian. So the distribution is like a, it's like a bell-shaped curve. If you now plot the same distribution, you plot the distribution of phi of Y. Well, if Y is positive, it just passes through the nonlinearity, so nothing changes. But if Y is negative, it gets like truncated, it gets set to 0, which actually puts a Dirac mass on the origin, if that makes sense. So if the input is positive, it just is unchanged, but if the input is negative, it gets set to 0. So it's like this is a mixed distribution, which is part discrete and part continuous. And this is referred to as a rectified Gaussian distribution. And you can look up what the variance is. And it turns out that, so while the variance of Y was equal to sigma squared by assumption, the variance of phi of Y is equal to, approximately equal to sigma squared over 3. So it's like actually a more complicated expression that involves like pi and some other stuff. But basically you can think of it as the effect of the ReLU nonlinearity is to divide the variance of its input by 3. So what this DeepMind paper does and what this other paper did, but is what they do is they say, instead of using ReLU, we're going to use a different nonlinearity, which we can just call phi prime of X or of Y, which is equal to like √3 times ReLU of Y. So the idea is that ReLU is squashing variances by a factor of 3. So you just put that factor back in, and it means that now this thing will like transmit the variance like without squashing it. So that's why we're calling this non-linearity design, because it's like thinking about the effects that the non-linearity has on the scale. What effect does the non-linearity have on the scales of the network? And like, if you want to get rid of batch norm or like these explicit normalization techniques, like this is the stuff you have to pay attention to. Okay. So there's like one more topic that I want to talk about, but yeah, if anyone has like more questions at this point. Okay. So yeah, this lecture is kind of like jumping around a bit and like introducing like a variety of different tools, but the rest of the lectures are going to be more like focused on individual topics. But yeah, this one is jumping around a little bit. But the next thing to talk about is, and the final thing is perturbation theory. So what this is asking is, well, you have a neural network, which we illustrated, like, which we noted, the notation is like this. So you have an input, you have a weight vector of all the weights in the network, and you get the output F. Well, when we're training the network, what we're doing is we're perturbing the weights. So we're like adding some perturbation delta W. And what we're really interested in is how perturbing the weights changes the function. Because if we could know that, that's actually what we care about when we're like doing things like setting the step size. We don't want to like completely change the properties of the function every iteration, because that would be unstable. Well, like that's the kind of argument that we're going to be making later on. But perturbation theory is like the study of this kind of question, like under a perturbation to the weights, delta W, like how does the function change? And this is ultimately, this is going to have to depend on like what is the architecture of the neural network, like how many layers does it have, and all of this kind of question. So like what I would call like, well, a lot of work does is it makes like simplifying assumptions. Like it assumes that like delta F, by that I mean like the change in the function, like the difference between the perturbed function and the unperturbed function. A lot of work will make an assumption that like delta F, the norm of delta F is bounded by the norm of delta W times a constant. And then if you make this kind of assumption, you can, like the change in the network output is bounded by like the size, the Euclidean size of the change in the parameters. Then you can like prove a lot of results. But the point is that this completely neglects like any information about the network architecture, or it doesn't involve neural networks really. So that's what we're going to try and like begin to go beyond when we talk about perturbation theory now. So if you look up perturbation theory, there's like a lot of results on like, for example, matrix perturbation theory and like perturbation theory of linear operators. So in that context, what this means is that like you have a matrix A, you have a perturbed matrix A plus delta A. Right, how do the properties of depend on, so how do the properties of the perturbed matrix depend on the perturbation? And like there's two kinds of results. So there's like the kind of result where you like assume that like that the perturbation is small, and then you can get these things called perturbation expansions, which is basically like a Taylor expansion. And like the kind of result that I just want to like give you a sense of like the kind of results that people have or that are there. And like a standard one is like you're interested in the ith eigenvalue of A plus delta A. And this is approximately equal to, and like the result is that this is approximately equal to the ith eigenvalue of the unperturbed matrix, like plus a linear function of the size of the perturbation. And then there's like another kind of result, which doesn't make the assumption that the perturbation is small. And these are called perturbation bounds. And an example of this result is like the statement that the norm, the Frobenius norm of the perturbed matrix is bounded by the Frobenius norm of the original matrix plus the Frobenius norm of the perturbation. So this is right, this is just the triangle inequality, but you can think of it as a perturbation bound. Okay, so the next thing that we're going to do is like look at starting to try and derive this kind of bound for a neural network. So, and like the point of a neural network is it's like deep and it has a lot of layers. So like that's the structure that we're going to focus on. And I'm going to do like the absolute simplest example here, and then like there's going to be a slightly more complicated example in the homework. But we're going to consider something called the deep linear scalar network, which is defined like this. So it's just a product over weights, which are all scalars, and then times an input, which is also a scalar. So it's like a big product, but it reflects like the kind of compositional structure of a network. That's like really the only similarity between this and a neural network, is that it involves products of weights. And then in the homework, you're going to generalize this to the case where like these are all matrices. But for now, like this is just a big product of numbers. And we're interested in this thing delta F, which is like defined to be f of x of w plus delta w minus f of x w. So how does the function change under the perturbations of the weight? So like remember, this w is a vector and delta w is a vector. And it also like it's kind of natural to like measure the relative size of the perturbation. So we'll call this, we'll divide this thing through by the unperturbed function. Okay, and then because the network has such a simple form, we can just like evaluate this thing really easily. So like the first observation is that because the input is just a scalar and everything is a scalar, you can just like divide out the input. So like the perturbation structure doesn't depend on what X is. And then you can also just divide 3 by the weights. So then what you end up with is this thing, which is like 1 plus delta Wi over Wi minus 1. So because the structure was so simple, we can actually just like, this is all just, everything here is an equality. You don't even need to like use any bounds. But the idea is that what this has done is it's connected the relative change in the function f so yeah, this thing that we've called delta f over f is the relative change in the function to the relative change in the weights. Which is denoted like delta Wi divided by Wi. And the fact that the formula involves this like this product is like reflecting the fact that like the function we were considering involves a product. So right, my claim is that if you want to know how to set the step size for neural networks, you're going to need to like think, like we're going to look at this in like the 3rd lecture, but you're going to need to like think about this kind of stuff, because it's actually like for the given architecture that you have, like what does the perturbation of structure of the weights have to do with the perturbation structure of the function? Okay.
Can I comment really briefly?
Yeah.
Yeah. So when you do something like gradient descent, what you're doing is you're computing a local linear approximation to the objective function, and then you're moving in that local linear approximation to the objective function. You're moving in the direction of steepest descent until you no longer trust the local linear approximation. And the tuning of the step size, in some ways, is about understanding at what point do you stop trusting the local linear approximation that the gradient gave you at a certain point. And so these tools that Jeremy has introduced will help us reason about that for deep neural networks.
Right. Yeah. Yeah, it's gonna, so I guess if like that is what we're gonna get to, but if that doesn't make sense now, don't worry, because like we'll go through that. But for now, just like, yeah, like it's important to know how changing weights change the actual function. Like hopefully intuitively that's important, but yeah, we'll try and like connect that to optimization. Okay, so this is pretty much it now. So the summary of what we did today is that was all that intro material, and then we looked at like global properties of architecture. By that I mean things like network topology, like things like CNN versus MLP. And we didn't really have anything conclusive to say other than like intuitively, if you have image data, you should use a CNN. But in later lectures, we're going to try and like have better things to say. And then we talked a bit about architecture search, but we didn't really like go into detail on it. And then we looked at local properties of architecture. And by that, it was like how to scale the weights of a neuron and how to scale the nonlinearity. Right, to ensure that the whole network activity is balanced. Right, and then the final thing we looked at is like how perturbations to weights. Well, okay, we'll say like perturbation theory. So in particular, like how weight perturbations affect the neural network function. So although we did it for a really simple example, like the sense I want to give you is that final thing is like the first connection between weight space and function space of a neural network, which is like something that you really want to do to be able to understand more about neural networks. So next lecture, we're going to go over like a possibly much deeper connection between weight space and function space. But so we're going to look at something called the neural network Gaussian process correspondence. And like there's some, this is like quite a cool result, but there's some general claims like things that we can say. So it connects the weight space of the network to the function space. It allows us to formalize what we mean by like inductive bias, or at least one definition of inductive bias. And yeah, we can start to talk about what kinds of function are common, or what kinds of function a neural network tends to implement. So you may have heard that like a neural network can fit any function, and people talk about these like approximation theorems where they say like, yeah, a neural network is a universal function approximator, but there's something that's like too good to be true about that. And I think that this is formalized by the neural network Gaussian process correspondence. So it says that although a neural network can implement any function, there's certain kinds of function which it much prefers to implement. And we'll formalize what that means next lecture. Okay, yeah, that's it. Thanks for listening.
Time for any questions?
Hi. I was wondering if you could talk a little bit more about why it's important to ensure the network activity is balanced. Is it because of like vanishing gradient problem, or?
Right. So the thing with the vanishing gradient problem is that it's something that people talk about, but I'm not convinced that it's like ultimately is the problem, or whether it's just a symptom of a different problem. And like, it's bad if things are exploding or vanishing, but you can always say that if the gradient's vanishing, you could just scale it up. So it's like, it doesn't really explain what's going wrong. So that's why when I introduced it, I just said it's like a heuristic that the different nodes should be on the same scale. And the empirically, it's like incredibly successful because like it's the basis of batch norm, which is just like used almost ubiquitously. And even without batch norm, I think it's like the basis of the initialization schemes, like Xavier. So what I'm saying is that like I take, for me, like at least the way I've like resolved it in my mind is that I take that as like the heuristic that it's good to have different neurons being balanced and on the same scale, and that there's like empirical evidence for that, things like batch norm and these initializers. And I don't believe that. I would rather think that vanishing gradients is a symptom of like this problem rather than the other way around. Like you get taught that like you have to be careful about vanishing gradients, but like I personally don't think that that's like a rigorous thing. But yeah, like it's definitely bad if the gradients are vanishing, but it's not clear that it's like you shouldn't be able to recover from that by just rescaling the gradients. It's like, yeah. Like to be able to say that vanishing gradients are bad, that is like a statement of optimization theory, or like that would need to be based on an optimization theory. But like we haven't really got to optimization theory. We're just talking about like good ways to actually condition the function space. Yeah, I don't have anything better to say than that, but like, I'm not convinced by some of the explanations people give for these things, and I think it's a good thing to like investigate and to think about more carefully.
Hi, Jeremy. I have a question on the normalization. So I come kind of from a model reduction background, and there we're looking for, so I study fluid mechanics, so we're looking for like say features of the flow, and we're looking for a minimal number. And when you said we normalize all the features, to me it seems like then we create kind of artificial features that are of the same weight, whereas we could have a more minimal number of features. So is this the right way to think of what neurons are representing, or am I misguided?
Well, what do you mean by feature? So yeah, sorry, go ahead.
So like, for instance, in fluid mechanics, there's like a flow past a cylinder. So there's like an oscillatory feature, and then there's just a constant feature. And you could reconstruct the field, the velocity field, just by applying some amplification to this time varying feature.
Okay, so you're thinking of activations in the network as being features, and that by rescaling them, you're somehow like changing the nature of the feature. And like that this you actually want there to be scale information because like right, but like my claim would be that I think that yeah, it's not really clear whether you want that freedom to have like activations varying over orders of magnitude, like at intermediate layers in the network, even if you did want that at the output.
But like I remember in CS155, we saw what the neurons represent for convolutional networks, and they would represent like certain features in the image, right? Isn't that something we want to preserve?
Right, but I mean, usually that it's just like you just care about things at the level of like you only want to know like is that feature present or not. So it's like enough to like have it kind of being on or off, not needing to know like distinguishing between like is that feature present like to this order of magnitude or to this order of magnitude. At least that's the understanding I have.
Maybe I can comment briefly. So if I understand, you hope to interpret the neurons in this neural network and extract insight from it. That's sort of what we covered in CS155 in relation to interpreting the neurons in the convolutional layers. This class will be looking at neural network theory that is completely orthogonal to that. And it's simply about how well do these complex function classes generalize, and how easily can you train them. That example in CS155 is after you've trained the convolutional neural network, try to interpret it. It presumes that you were able to train it. So your question is a valid one. How do you get everything you want? But the theory in this class will be largely ignorant of interpreting the semantics of the concepts learned in the neurons.
Right. But I guess I think that the question was like, is somehow imposing these constraints that are designed to like not let like certain neurons be too large in activity. Is that not somehow limiting like the kinds of functions that it can represent and the kinds of functions you would want it to
I think
be
it can
able to
distort the interpretability of what the neuron is semantically extracting from the data set.
I mean, do you remember, I don't know, have you ever looked at this, like the variability, like in an experiment like that, like how much variability that actually was between like this magnitudes of different neurons?
This sounds like a great final project for the class, by the way. Something in this
Right.
space. Yeah.
Yeah, I guess that you may be right in the end. Like I'm presenting like my best understanding, and that like I've done experiments and like imposing these constraints seems to not impact the performance of these networks and actually improve them. But it is possible that
Right. It's not about the final prediction performance. It's about whether or not you can interpret the neuron. Like, you can find the dog neuron in a convnet, right?
Right.
It's about interpretability, not final performance.
But if like the results of an interpretability analysis change based on like applying some constraint like these, like doesn't that mean that like it's not clear the interpretability analysis was telling you at least the results of your analysis weren't like a kind of necessary feature? It was just, do you know what I mean? It's like if the analysis is like sensitive to things which actually don't affect the performance, or
well, I think interpretability is subjective. The human's ability to sort of understand the semantics of what's happening depends on the representation of how you present the data. And if these types of transformations compromise that, then it could, nothing could change in terms of functional power, but it could change in terms of human interpretability. Again, I agree with you, Jeremy. This is an unresolved question, and it actually does sound like a great research project for the class.
yeah. Yeah, absolutely.
Okay, stop the recording.